Hello and welcome to this bare metal programming series where we're building firmware for a cortex-m STM32 microcontroller. Now, this is not a full episode, this is a kind of micro in-between episode, and today what I want to do is to just zoom in on one specific concept, kind of two in a way, very shortly, just to highlight something that's quite interesting that I didn't really have time to touch on in the previous episode, and that's something that I got a couple of different comments about from people. So I think it's worth taking a look, and I think also it highlights something interesting about both the C programming language and kind of a practice that you can get into when you're doing firmware or you're doing low-level programming, which is kind of getting used to and comfortable with the idea of reading and understanding the assembly code that gets generated from your C code. Now, you don't have to be an expert on assembly, you don't have to really know too much about it. I'm going to walk through the instructions that we end up looking at, and there are only a couple today. But yeah, I think it's going to highlight something interesting. So let's take a look. So if I open the bootloader.c file that we wrote last time, well, basically in here, as a very, very small recap, what we're doing is kind of calculating the address of where the main application begins. And it just so happens that where the main application begins, that's also where its reset vector is. That's also where its vector table is. And not the first, but the second entry in the vector table is actually the reset vector. And that is kind of the first piece of code that's supposed to execute in the main application. And so what we're actually doing in this extremely simple bootloader is just, in our main function, just calling this jump to main function, which is jump to the main application, actually. It's kind of weird because we're in main and we're saying jump to main. That you would think that's an infinite loop. That's my bad in naming. So what we're actually doing is we're kind of computing a series of pointers and then casting kind of the final result of that to a function pointer, and then we're calling that function pointer. So this is kind of, in C, you don't get direct access to the registers and all of that kind of stuff. So the way in which you can express this idea of like going and finding that address in memory and interpreting it in a certain way, like this is kind of the most sort of direct but also verbose way of doing that you can do. And quite rightly, someone pointed out that, you know, there are probably nicer ways to do this too. And well, I chose to do it this way because I thought laying it out kind of step by step would make it obvious what's happening. But let's actually look at a couple of different ways to do it and the assembly that gets generated for each of those possible ways. So first and foremost, let's just look at the assembly that's already generated for this. So as it stands right now, the way we can do that is to use the arm none eabi obj dump command. And this is just dump from an object file. We're going to be dumping the the assembly output from the elf file. So basically just the disassembled, not disassembled, but the assembly code that comes out, the disassembled code that comes out from that. And we get that from the bootloader elf. So the elf contains all of the information about this program, including symbol names and references to from an assembly instruction to a line in the C code, all of that information. And we can use several commands to extract information from that elf. So I'm just going to redirect this to a file called asm-dump so that we can just look at it in the editor. And I'm going to open that up and get some kind of syntax highlighting here. I'm not exactly sure which language it thinks this is, but this kind of looks nice. So what we're seeing here is a representation of the assembly. So on the left, in this column, we see the address that we're currently talking about. So you can see this is the beginning of Flash. You can see the symbol name that relates to. So most often this is a function. In this case, it's the vector table. So it's not a function. It's a big data structure. It just contains a whole list of addresses. But you can see that this is the raw value in this column. And this is the assembly that the disassembler is trying to attach to this. And we know that the vector table, this doesn't make sense, right? This isn't real assembly code because this isn't code, this is data. But what we'll see here is that this is a RAM address. This is actually the first entry in the vector table. That's what the stack pointer should be set to when we begin execution. And the second is the reset vector here. So yeah, I mentioned briefly in the previous video that addresses that end in, like the addresses that have a bit for their 1 set, like the 0th bit is set to a 1. That's not actually a valid address, but that is something that the ARM architecture uses in order to recognize in which context this is supposed to be executed in. So if that 1 bit is set, the 0th bit in the 32-bit address is set, and we branch to that address, that actually tells the CPU to go into thumb execution mode. So if we were to search for this address, we wouldn't find it, but if we searched -1, so get rid of that 1 bit, well, we'll find the reset handler. So that makes sense, right? That's the reset handler. What we want to look at is the main function. So I'll just type in main up here. It happens to land just after the reset vector. And you can see that main is a very, very simple function. Now, if I were to search here jump to main, we wouldn't find it because the compiler has actually optimized that function away. The compiler has looked at our C code. It's seen this call to jump to main. It's looked at the fact that jump to main is, well, it's quite a short function, so, you know, it can just inline it, so to speak. But also it's marked as static, which means that no other places in the program can see this function. Only this file has kind of visibility of this function, and this is the only place it's called. So why bother to create a whole function? Let's just stuff it into the main function instead. So that's what the compiler's done. And the first thing that happens in this function is that it actually pushes some registers to the stack. So it pushes R3 and the link register, which is kind of where the return address of the function is. So it just, and this is customary, right? So we push R3 and we push the link register, and then we can actually do anything in the program. We can also modify those registers, and we don't have to worry about, like, well, we messed up their values, right? But it's quite a nice convention. This is something that the compiler does, right? This isn't required. You can have functions that don't exist in this way, and if you handwrite assembly, like, you're not required to do it this way, but this is something that the compiler will very often do. And the nice thing is that's kind of symmetric, because at the end of the function, the compiler will do the reverse, right? So it will do a pop, and it will pop the R3 value back in, and the link register value, well, that will end up going in the program counter, right? Because we're returning to that address. So you can see that this pop here, with the link register value going to the PC, that's just essentially a return instruction. So it's pretty interesting that ARM is able to stuff this into just 16 bits. This information ARM is a really interesting instruction set. And if you followed along with the RISC-V series, well, RISC-V is really beautiful for how simplistic it is and how much elegance there is in the instruction encoding. ARM is a really impressive instruction set in the sheer volume of interesting and useful stuff that it's able to cram into these instructions. It's much more complicated than RISC-V, but it's very, very powerful and sort of like dense in terms of what it can do as an instruction set. So, all right. So the actual content of the jump to main function, that's actually just these 3 assembly instructions. So the first instruction is load into register. The register that we're going to load into is R3. The compiler has chosen R3 arbitrarily. So we're going to load a value into R3, and the value that we're going to load is the current program counter, which points at the next instruction, so this one. The current program counter plus 8. And it's not just that value. So we're not just calculating that value. We're then, these square brackets, they indicate that we're going to read the value that's at that address. So if we treat that calculation as an address, we're then going to take the value that we find at that address and stuff it into R3. So let's just figure out what that address should be. So the next instruction, that's this address. So let's just open up node arbitrarily. So that's this address, B0 plus 8. Well, of course, that is just 8000, 8000, 1B8. And that makes sense, right? B0 plus 8. That puts us down here. And that's kind of interesting, right? This is not, in fact, an instruction. This is data. And if you look at the value that's actually represented there, 0800, 8000, that is in fact the main app start address, right? That is the flash base address, this address here, plus hex 8000, so the size of the bootloader. And this is something that compilers will often do when generating code, is if there is kind of constant data associated, like just with that function, actually, it will often just sort of cram it somewhere in the vicinity of that function. I think this is for caching reasons, for like efficiency's sake, like you don't just put it in another random place, but instead put it close by the function because you've already kind of loaded up a bunch of things from that location. That's I think that's true. I'm not 100%. But basically, we end up with this value. So we take this value and we stuff it in R3. That's what this instruction does. And this is kind of another example of ARM having a really dense and interesting instruction set, is that a lot of the functions, a lot of the instructions in ARM are able to kind of take an operand, an argument, and like offset that with either an addition or with a shift operation, or, you know, there's a whole multitude of things that can happen there. And that's pretty cool, right? That allows you to sort of do add, shift, also a kind of multiply given the shifts. So you can actually calculate a lot in a single instruction just by kind of shifting around. And of course it's limited to how much shifting and adding you can do, but if you kind of have small constant offsets, that's something that the compiler can take advantage of when it generates these instructions. Okay, so the next instruction here. So now keep in mind, this is just this is now the beginning of the vector table. So it's the main app address, and it's also the beginning of the main app's vector table. So basically pointing at this, but for the main application. And of course, what we want is like the reset vector. We want this entry in the table. So the second entry offset by 4 bytes. And so of course what you see is that it's just another load into register. We're also loading again into R3 because why not, just reuse it. This time the address that we calculate is what is currently in R3 plus 4, right? And of course that's exactly what we're doing here to figure out the reset vector entry. But again, we actually read the value at that address. So the entry is just kind of is a place in memory. The value inside that entry is actually the address of the function, the reset handler. So we're going to read that, and now that address goes into R3. And that's something that we did kind of in this second C statement, right? So we have the reset vector entry, and then here we read the value at that address, and we kind of treated that again as a uint32 pointer. And then finally, we branch, and this is a branch instruction, a branch and link, and we branch to the value in R3. So this is our jump to jump function. Right, we've cast it to this function and we're calling it. So that's what's happening there. And we actually don't ever expect that this function will return, so the rest of this will never execute. But yeah, that's it. That's what this does. And it's really simple. So in fact, this whole C function is 5 lines of code, but in fact, it's 3 assembly instructions. Of course, we could make this shorter and we could put all of this on one line, but keep that in mind. Okay, so that's the assembly. That's how it works. It's quite straightforward. It's, in fact, I think conceptually easier to understand in assembly than it is in the C code. But let's just see what we can do to improve this, right? Improve the C code representation. So the first thing we could do is, instead of having this hard-coded 4, we could instead use size of uint32. This would be a kind of nicer way of doing it, just because it removes a magic number. Although the magic number is relatively obvious what it's doing in this case, this is pretty clearly saying, whatever this address is, plus 1 integer, right? So we're moving to the next integer. So if we compiled this, it would produce exactly the same code. I'm not even going to do that because this will literally just become the number 4 before it even sort of compiles there. But of course we can improve this a little bit more. So instead of doing this whole song and dance and offsetting manually and recalculating pointers, well, instead what we could do is let's make a uint32 pointer, and let's just call it main vector table. So the main vector table is just this address, right? So that's what that is. We're doing exactly the same thing here, except we're not offsetting yet. So then the reset vector entry is just to get that to that thing, we can just treat this as if it's an array. And in C, you can always treat pointers as if they were arrays. And so if I put an index of 1 in there, it automatically sort of takes the 4-byte step to the next item in the array. So this is something which causes a lot of bugs in C as well, right? Because if you have a pointer that doesn't actually automatically make it an array, right? It doesn't mean that there is an item afterwards, but you can always do this, right? This is kind of something that's possible. So this allows us to get to the main table, and then of course we actually want the pointer to this thing, right? So we can then just use the normal address of operator to get that, right? So this is kind of a little bit cleaner than doing all of the casts. And then finally, to get to the reset vector, well, then we have to read what's at that and cast it back to a uint32 pointer. So what we could actually do here is, what we're doing in this case is already reading it, and then we're trying to go back to the address of what we've gotten there, the table. So instead, what we could do is this actually is the reset vector address. So here, instead of doing this, we could just do this. And then of course, we just calculate the jump function again, and we jump to it. So let's try to compile this and compare the assembly output. So I'm going to make clean just to make sure that it really does regenerate the code, although it will if we just run make. Then I'm going to do the same object dump command, but I'm going to add 2 this time. So we actually generate to a different file. And if we scroll down here to the main function, well, what we're going to see is that nothing changed, right? It's exactly the same assembly gets generated, right? This is still the same operation that's happening, and we still end up with the same constant data down here. So this is really just another precisely the same way of expressing the previous program. Maybe in a slightly better way, actually. So one of the other things that we could do here is that we don't need really to go through this second indirection step, right? We don't need to cast this to a uint32 pointer only to then cast it to a function pointer afterwards, right? We could already just do that here. So if I run make obj dump, and then we'll go to 3, and we scroll down again, exactly the same assembly is generated. So this is now an even, like maybe an even better way of expressing this. And of course, if we wanted, we could sort of put this number 1 in a define and say that this was the reset vector. So we could kind of sort of progressively clean this up. And it's gotten a little bit shorter now, so this is probably a better way of doing it. What I want to show you now is what I think is probably the best way of expressing this in terms of just the most kind of C-like way of doing it, but also what I think is a really expressive way of doing it. And so for that, we're going to bring in a libcm3 header. So I'm going to bring in cm3 vector. And let's just open this up for a minute. We did look at this in one of the previous episodes, but basically this defines kind of the reset vector. This defines I keep saying reset vector, I mean the vector table. It defines the vector table as a type here. And then every entry of the reset vector table, the vector table, is a void pointer, right? You can see that this is exactly the same, void function define that we made in the previous one. This is a function pointer that returns no arguments and returns no value and takes no arguments. So every one of those is just a thing. And what we say is that somewhere there is something called a vector table that actually gets defined in a different place, but basically libcm3 defines a structure for this, right? A sort of object definition, so to speak. So what we can do is we can take this object definition and go back to the bootloader, or we can get rid of this void function definition. And instead of saying that our main vector table is a uint32, well, instead, let's say it's a vector table t pointer, and then we're just gonna cast our main app address to that. And then instead of doing this whole void function song and dance, what we'll do is we'll just take our main vector table and call the reset function on that. So this is now you making some use of this type that we have. We're basically just saying this address, actually it's this structure, right? This address points to this structure in memory. So basically look at this, like whatever you find there, it looks like this. This is how it's laid out in memory. You do have to be a bit careful with doing this, like casting a memory location to a struct, because structs, the compiler by default will insert padding between fields in the structs if that's necessary. And when I say if that's necessary, what I mean is that there are some rules that define when it should do that, and most often it's when your data does not align to like a natural boundary of what you're trying to access, right? But in this case, every one of these items is a uint32, right? So like it's 4 bytes wide, every item. So there's no padding in the struct. So what we can say is that, hey, that address in memory, it is just this structure. So it's precisely what we did before, right? We just said this address in memory is a uint32. We could have said that address in memory is a uint8, right? It's an 8-bit value. But now we've said the whole thing is just this structure. And then we can treat, like once we have that structure, we can just interact with it as a normal C object, just like normal, right? And then it's already told us that what it finds at the first entry in that table is the reset vector. Let's just call it as a function. So let's do this for the last time. Make, and we'll just do the 4th object dump, and let's open that up. Scroll down again. And what do you know? We have exactly the same code again, right? Because effectively we're doing the same thing again, right? Like in every one of these iterations, we've written the C code slightly differently, but the thing that ends up representing in actual instructions that are executed on the CPU is always the same, right? We're figuring out this address, we're figuring out an offset, we're reading the value, and then we're jumping to it. So for me, this is a really useful tool, kind of being able to look at the assembly that gets generated, to change the C code you put in and see what comes out on the other side. I think this makes you a better programmer in general, because you are not allowing sort of a layer in between, right? It's fine to say, I don't need to read the source code of the compiler and figure out every optimization that it makes, but it's good to be able to, you know, almost like smoke test the thing, right? Like say, okay, I think if I make this change, it will result in this. See if that assumption is true. This allows you basically to test your assumptions. So I hope this kind of has made clear, like, that skill and that debugging possibility. Practice that, try it out, learn about ARM assembly. Just look up the opcodes, the mnemonics here. If you don't understand what they are, if you don't know what MOVS is, just Google it, MOVS ARM. You'll be able to find out what that does. But also I hope that it's made clear the idea that, you know, especially when we talk about pointers and things in memory in C, that really there is no true conception of a type in memory. Like, memory is memory. It's raw. It's like a sequence of bytes or 32-bit words or whatever. But it's really just information, and like the layer that we put on top of that information is what makes it what it is. So, you know, when you write your code, just write the code in the way that's the most expressive for that. Just try to write code that you think makes sense, and just check to see that the compiler is going to generate something useful from that. That's kind of all I want to cover for now. I said it was a short video. I think it's a little bit longer than I wanted it to be, but I hope it's valuable. So bye for now, and I'll see you in the next one.